All right, well, welcome everyone. I am JJ. Let's just jump in and do an example problem. So in this one, we have a force of 875 newtons is applied to our pipe as shown. Let's determine the moment that our force here is going to cause about the origin. And we're going to give our moment as the Cartesian vector, and then we're going to give the magnitude as well. So part of our goal here is we've been working with coordinates to get position vectors, unit vectors, force vectors. Remember, there are other ways we can find x, y, and z components of a force. This is really just trying to reinforce that. So we have alpha, beta, gamma angles on this one. We could also give like the azimuth and transverse angles. We could get to x, y, and z components that way too. But let's just jump in and do this. If we remember, if we're trying to get our Cartesian vector, I need x, y, and z components. My fx I can say is really my total force times the cosine of alpha. Putting in our numbers in here, our total force is given 875 newtons. So 875 times the cosine of alpha, cosine of 110.8. Cosine 110.8. Our next one we can get, or let's evaluate that. This is going to get us to negative 300.4 newtons. From there, we can come in and get our y and z components. Really just following that same process. Our force in the y direction should be, well, I can say it's my total force times the cosine of beta. F cosine beta. By definition, this is going to be true for us. So this is 875 is still my total force. Cosine of beta, cosine of 46.64. 46.64. Or this is going to get us 600.8 newtons. And then finally, a similar process for our z component. That force in the z direction should be our total force times the cosine of gamma. If this is not at all familiar, maybe take a look back at some of our previous videos when we talked through 3D vectors in here. We've really broken that down before. But this is our total force, 875 times the cosine of gamma, 50.14. 50.14. Remember, alpha always measures from the force to the x-axis. Beta measures from the force to the y-axis. Gamma goes from the force to the z-axis. This is going to get us here 560.7 newtons. 560.7 newtons. Really, that's an x, y, and z component, or I have I, j, and k terms in here. That's really all that I need. Or that's one line in my matrix. The other one should be a position vector that goes from the origin, from whatever point I'm taking moments about, which we are told to use the origin, to some point on our force vector. And the only one we know here is the back of that force. So I'm really coming in and saying to get that moment about my origin, I need the cross product of a moment arm vector, so a position vector, that goes from whatever point I'm taking moment about, from the origin to any point on my force vector. And I only have coordinates to get me to the tail of this force vector. We're not given a name for that point, so I'm just going to say ROF, from the point I'm taking a moment about to the force vector. And we'll cross that with our force vector, crossed with F as a vector. And I can fill in my numbers for that. My moment about the origin should be, remember, our top line is every single time IJK. So we'll fill that in. IJK. Our second line should always be our moment arm vector. I'm going to convert this into meters instead of millimeters, mostly because Newton meters is a more common unit at this point than Newton millimeters. But I'm just dividing by 1,000. So in the x direction, I've gone out 200 millimeters would get me there. I'm just tracing the path. That is 0.2 meters. In the y direction, I'm going 250 millimeters, converting to meters, 0.25 millimeters or meters. And finally, up in the z direction, we're going up 150 millimeters. So that'd be 0.15 meters. If you left this in millimeters, if you were my student, I wouldn't mark you down. It's an equivalent thing. It's just a unit conversion. It's really all we've done here. It also keeps my numbers from getting gigantic. When I get a really big number, 300 times like 200 for my millimeters, I start getting huge numbers. I'm likely to just make a calculator mistake, miss a digit when I'm writing down my answer, or punch something into my calculator wrong later. Doing that quick and easy conversion helps me be more successful. But let's fill in our force vector. So we can take our x component, negative 300.4, and fill that into our I position. Our y component will go with j, so 600.8. And finally, our z component goes to k, 560.7. And that's it. We've gotten our matrix filled in. We can come in and cross multiply to evaluate that. So this is going to get us equal to, we'll start with our I component on this. So I times, we'll ignore I's column and I's row. It leaves us with just this 4x4 piece left, the J and K components. And we'll always do our top left, 0.25, times our bottom right, 560.7, minus our top right, minus 0.15, times our bottom left, 600.8. And then we go to our next one. That is our whole I component. We'll evaluate that later. We always subtract off J, minus J. Again, we subtract J so we can do that top left times bottom right, minus top right times bottom left. It makes the math work out correct for us. Always subtract J. And then again, we'll cross multiply this. So times, ignoring J's column and J's row, we have just the I and K pieces left in here. So our top left I would be 0.2 times our bottom right, our K piece, 560.7, minus our top right, 0.15, times our bottom left, negative 300.4. And then one last time, we go back to our K. When we go back to K, we add again. So plus K times, we ignore K's column and K's row, looking at just the I and J terms in here. Our top left will be I, so 0.2, times our bottom right would be the J term, 600.8, minus our top right times our bottom left, 0.25, 0.25, times bottom left, negative 300.4. We just need to evaluate that then. Punching that into our calculator, just one line at a time in here. I'm going to get to my moment about the origin, MO. This is going to be one of my answers in here, is our I component works out to be 50.1. 50.1. Our J component will get us to our 50.1 I. Our J component is negative 157.2 J. And our K component, when we evaluate it, is going to be plus 195.3 K. And our units are Newton meters for the entire thing in there. But that would be our first answer. What's my moment as a Cartesian vector? Express our moment as a Cartesian vector. And then we need to get our magnitude of the moment. The magnitude should be an easy step for us. It's just using the Pythagorean theorem. Again, if we hadn't converted to meters, we just have 1,000 times greater than this. When we get to our magnitude step, those become really big numbers that we're putting in. But it's an equivalent answer. It's fine to do that. But our magnitude of our moment should get us to the square root of our I component squared, 50.1 squared, plus our J component squared, plus 157.2 squared, plus our K component squared, plus 195.3 0.3 squared. All together, that's going to get us that our magnitude here, the magnitude of the moment is 255.7 Newton meters, which is our final answer for our problem. Again, we can get through this. We can split this up using coordinates if we had them. We could split this up using alpha, beta, gamma angles. Use those theta, x, y, theta, like the transverse and azimuth angles that everybody hates. There's multiple ways to get our components here, but let's just make the matrix, evaluate it. Be careful with our signs. We can get through this. If this was useful for you, hit that like and subscribe button. Let's get you in there with JJ.